In section 3.2, we're going to look at perfect squares, perfect cubes, and their roots. Let's take a look at a Rubik's Cube. A Rubik's Cube has an edge length that is 3 units long. So how could we calculate the area of one face of the cube? Well, if we take a look at our cube, each edge face is 3 units. To find the area of one face, we'd be looking for the area of this square here. So the area equal to the length times width, which would be 3 times 3, which would equal 9. So why is this number 9 considered a perfect square? Well, if you look at the factors of 9 and the prime factors of 9, 9 is 3 times 3, which is really 3 squared. So therefore, we can say that 9 is a perfect square. Now, if we wanted to find the volume of this Rubik's Cube, to find the volume, we would have to go length times width times height, which would be 3 times 3 times 3, which would be 27. 27 is called a perfect cube. And why do we call 27 a perfect cube? Well, I'm sure you answered that 3 raised to the power of 3 is 27, so 3 cubed is 27. So therefore 27 is a perfect cube. All right, a perfect square. Let's talk about perfect numbers here. A perfect square is a number where the square root is a whole number. For example, the square root of 9 would be equal to 3. The square root is denoted by this little 2 inside the notch with a radical sign and a 9 underneath. And we'll talk about the terminology of those things shortly. Now, if the 2 is written there or not written there, it's assumed to be square root. A perfect cube is a number where the cube root is a whole number. So for example, the cube root of 27 would be equal to 3. And the notation right here with a little 3 inside the notch means cube root of 27. So if we take a look at roots, this whole thing is called a radical. And this number here that is in the notch is called the index, and this part under the radical is called the radicand. So again, the whole thing's a radical, the little number is the index, and the number under the root sign is the radicand. Now, if we're determining roots, we could break down numbers into its prime factors. So we can use our skills that we learned in sections 3.1. So let's say we want to determine the square root of 1296. Okay, so I'm just going to get a new page here. I need a little bit of room. So let's start with 1296 and let's break it down into its prime factors. Well, one possibility would be 6 times 216. And 6 breaks down into 2 and 3. 216 is 8 times 27. 8 is 2 times 4. 27 is 9 times 3. 4 is 2 times 2. And 9 is 3 times 3. So I have 1, 2, 3, 4, 5, 6, 7, 8 prime factors in my prime factorization. So if I was to write my factors out, it would be 2 times 2 times 2 times 2 times 3 times 3 times 3 times 3. Now, we were looking for the square root of 1296, so we want to group our factors in pairs because 2 times 2 is 2 squared, and we're looking for the square root. So therefore, for these two 2's, we're going to collect 1, 2. There's going to be another 2. These two factors is 3, and those two factors of 3 produce a 3. Now, if I multiply these all together, I get 2 times 2 times 3 times 3, which ends up equaling 36. So therefore, the square root of 1296 would be equal to 36. All right. Another application of using prime factorization would be trying to break down something like the square root of 80. Okay, so if I break down the square root of 80, again, if I use prime factorization, 80 would be 8 times 10, which would be 4 times 2 and 2 times 5. and 4 would be 2 times 2. So now I have 1, 2, 3, 4, 5 prime factors. And if I listed them, it would be 2 times 2 times 2 times 2 times 5. So the square root of 80 could be thought of the square root of the product of those numbers. Now, because we're dealing with square roots, I'm going to look for factors or pairs of the same factor. So 2 times 2 is 4, so I can take a 2 out. Okay, 2 times 2 is 4, and the square root of 4 is 2. I can take another 2 out. So therefore, in front here, I have 2 times 2, which ends up being 4, and I'm left with a radicand of 5. Therefore, the square root of 80 can be broken down into 4 times root 5, and these two quantities are equal. All right, I want you to take a second, pause the video, and I want you to try to find the square root of 1764 by using the prime factors. Okay, hopefully you've had a chance to try this one. Let's take a look. So I have 1764. And if you did the prime factorization, it would be 2 times 882. 882 is 2 times 441. 441 is 3 times 147. 147 is 3 times 49. And 49 is 7 times 7. So now if I list my factors, 2 times 2 times 3 times 3 times 7 times 7. And we're looking for the square root of 1764. So we want to group our factors in pairs. And for every pair, we can bring out 1. So it's going to be 2 times 3 times 7. So that equals 42. Therefore, the square root of 1764 is equal to 42. And yes, you could check that on your calculator by taking the square root of 1764, and you will in fact get an answer of 42. Okay, so now we're going to look at determining the cube root of 1728. So same idea as before. So we're going to start with our 1728, and we're going to break it down to its prime factors. So 2 times 864. 864 is 2 times 432, which is going to be 2 times 216, 2 times 108, 2 times 54, which is 6 times 9, 2 times 3, and 3, and 3. So if I was to list my prime factors, I have a total of 1, 2, 3, 4, 5, 6 2's. And I have a total of 1, 2, 3 3's. Now we are looking for the cube root of 1728. So now we're going to group our factors in groups of 3. And for every 3, we can bring out 1. And if I multiply those together, I'm going to get 12. Therefore, the cube root of 1728 is going to be equal to 12. So in other words, if I go 12 raised to the power of 3, I should get 1728. Okay, I want you to pause the video and give this one a try on your own. Okay, hopefully you've had a chance to try that one. So now let's take a look at the cube root of 2744. So again, we're going to break this down into 2 times 1372, which breaks down into 2 times 686, which is 2 times 343. 343 breaks down into 7 times 9, 49, sorry, and 49 is 7 times 7. So if I look at my factors, I have 2 times 2 times 2 because I have 3 2's, and I also have 3 7's, so it's going to be 7 times 7 times 7. So now we do our grouping. 2 times 2 times 2, because we're doing cube roots, I group them in 3's, and for every 3 2's I can bring out 1. For every 3 7's I can bring out 1, and 2 times 7 is 14. So therefore, the cube root of 2744 is equal to 14. All right, in our next example, we want to show that 648 is not a perfect cube. Again, as you're probably guessing, we're going to use the same strategy. We're going to break it down into its prime factors. 324 is 4 times 81. 2 times 2. This is 9 times 9. And this breaks down to 3 times 3 and 3 times 3. So if we list our prime factors, I have 3 2s and I have 4 3s. So therefore, if you list them in groups of 3, because we're looking for perfect cubes, there's 3 sets of 2, there's a set of 3 3s, but I have this 1 3 left over, and there's no group of 3 for that one to go to, so that proves that 648 is not a perfect cube. All right, the last question, or the second last question, sorry, says find the smallest number that we could multiply 1125 by to make it a perfect cube. Well, again, same idea. We're going to start with the prime factors of 1125, and we're going to break it down. And 1125 breaks down into 45 times 25. 45 is 9 times 5, and 25 is 5 times 5, and 9 is 3 times 3. So now if we write our prime factors, I have 3 5s, and I only have 2 3s. So if I do my groupings, because we're doing cube roots, I have 5 times 5 times 5, and I am missing 1 3 here to have a group of 3. So that means I basically have to multiply 1125 by 3 to make it a perfect cube. All right, our last example is a bit of an extension problem, and it says we have a cube, and the cube has a volume of 4,913 cubic inches. What is the surface area of the cube? Okay, well, the key word to this problem is cube, and we know that a cube, we talked about that earlier, has all side lengths that are the same. Okay, so if we take 4913 and we break it down into its factors, okay, we should be able to find its perfect cubes. Okay, so I'm going to break down 4193, and that works out to be 17 times 289, and 289 also breaks down into 17 times 17. And these three numbers are all prime, so therefore 17 times 17 times 17 is 4913, and therefore the cube root would be 17. So that means each side length of my cube is 17 inches. Now we want to figure out what is the surface area of the cube. Well, the surface area is the area of one face of this cube. So basically, I would be finding the area of that square. So to find the surface area of one face, it would be 17 times 17, and that works out to be 289 inches squared, because each of these is in inches. So now we know what the surface area of one face is, but we want the surface area of the entire cube. In a cube, we have a total of 6 different side faces. So I'm going to take 289 inches squared, and I'm going to times that by 6. And I'm going to get my answer of 1,734 square inches would be the surface area of my cube. So therefore, we write a final statement because we're dealing with the word problem, and we would say the total surface area of our cube is 1,734 square inches. Okay, so that concludes our lesson on section 3.2. So again, we're just using an application of prime factorization to find square roots and cube roots. So there are a few problems for you to try from your textbook. And if you pause the video, you can also copy down these two examples, and you can try and work those ones out as well for extra practice. All right, good luck with the assignment.